So I guess we should start. And so thank you very much, Gillian. She's going to be speaking on utility measures for synthetic data.
Thank you very much, Robin, and thank you particularly to the Newton Institute for allowing me to come along to this week's workshop in synthetic data, which has been fantastic for me. It's been great tossing ideas around and having a chance to sort out lots of things with other people in this field. And I particularly wanted to thank Mark Elliott, and you can tell him later on that I have thanked him when he arrives. So, this is very much work in progress. But here's Mark. I've just thanked you for running and for organising this workshop, which has been fantastic. This is, as I said, work in progress, and much of it is joint work with Beata Nowak and Joshua Snook, who are here. Particularly the earlier first bits, but some of the later bits, which are by no means worked out yet, are probably got quite a few errors, and those errors are entirely my fault. An outline, what I'm going to start by talking about is a bit of background about how Beata and I and Joshua are producing synthetic data for the Scottish administrative data. Just going to be very quickly going through the methods we use and then getting on to the main part of the talk, which is about utility measures. I'm going to be focusing mostly on global measures, particularly propensity score measures, but also extending that to measures taken from tables, and particularly to talk about how these relate. And I'm finally going to talk about some of the practical aspects of how they might be used by people who are creating synthetic data. So we've been having a lot of discussions this week about what are synthetic data. So here's my definition for today. It can be that it's altered data to protect its confidentiality, but it must be based on an original set of data. And the synthetic data are generated from statistical models in some very broad sense. And their purpose is to reduce the risk that records will be identified with individuals or other units. It doesn't have to be an individual, could be a business or anything else. And I'm going today to be discussing completely synthesized data. That's where every observation of every variable is replaced by something from a statistical model. So nothing real is left in there. Oh, sorry, that's the last one. Basically, they look like this. That's the observed data, and that's the synthetic data. We want them to look structurally like the original data, but contain only artificial data. Now, background of this is that the SILS project, which started in 2013, was to develop tools that the staff with access to the original data could produce synthetic data extracts. That was started within the Scottish longitudinal study. And the idea was that researchers could explore the synthetic data and develop their analysis code, and then bring their analysis code into the secure unit, or send it to the staff in the secure unit to run the analysis. Another use of it is for creating teaching data sets, but that kind of came on stream slightly later. Originally, we worked with the staff at the Scottish Longitudinal Study, and we still do. Though, in fact, it's only in the last 3 months that we've actually had permission to release synthetic data sets to users. So we've been working on it a lot, but we've been waiting for administrative permission, which we finally got. So we're now just doing it for real. But we also now have a wider remit within the Administrative Data Research Network in Scotland to work with the staff there to make other sorts of administrative data available. And in particular, we've developed the synthpop software tool, which is available online, not just for staff within these places, but for anybody to generate synthetic data. Very briefly, the methods used in synthpop involve building up the joint distribution of the synthetic data from a series of conditional distributions. Starting with a synthetic version of the first variable, this generated from some sort of fit to its distribution, most commonly a bootstrap fit. Then the next variable is generated from the conditional distribution of the next variable given the first variable and its synthetic values which are generated given the synthetic values of the first, and so on and so on. So we build it up. There's a lot of choices within synthpop. We can choose the distributions to fit to each conditional distribution, usually the same more or less, but we can do it individually. In particular, we can choose parametric methods as well as non-parametric methods, and our default is the cart method, and I'll be showing later on that we found that works really well. The order of the variables makes a difference, and we can choose the selection of predictors for each conditional distribution. And staff who have access to the original data have to make choices. They have to decide how to do it, and they have to be able to evaluate their synthetic data. So what are the parameters of the evaluation? There should be two parameters to the evaluation. One being the risk of disclosure, which we hope will be low, and the other one being the utility, which I have here on the x-axis. I'm sure most of you are familiar with this sort of graph. If you have random noise in the bottom left-hand corner, you have low risk but no utility. Up in the top corner, if you have unaltered data, you have high risk of disclosure but optimum utility. We're hoping that our synthetic data is sort of down here compared perhaps to other methods of alteration, and that we may be getting better utility for a lower risk, but that really has to be shown yet because disclosure risk methods for synthetic data, as we've known in this week, are not really very well worked out, though we are beginning to get there, and our discussions have helped. We do need good applicable measures, but that's not what I'm talking about today. In terms of utility, there are a number of ways we can do it. We can use graphical procedures, and I think these are very important. But we can also use measures of lack of fit of the synthetic data to the real data. We can compare results from statistical models fitted to the original and the synthesized data. I think that the first two of those should be carried out by staff creating the synthetic data. The third one, which I've put in brackets, the results of the statistical models, are something that happens at the end of a set of analyses. So we can't really expect people creating synthetic data to do that at that stage, although that's commonly what's produced in papers that evaluate synthetic data. We can't expect our staff to do the analysis for our users. So I'm going to concentrate on the second two here. Now, graphical measures. The first thing I think everybody should do is look at univariate summaries. And this is the sort of thing our package produces. These are graphs for marital status against age. The dark one is the observed and the light one is the synthetic. It's a big data set, several 100,000, and I think you can see that we've got very good agreement on marital status. Age looks more or less all right. This is historical data, so it's not the kind of age distribution we would get now. A lot more babies, not enough older people. And a big fall, possibly due to infant mortality. But we can see we've got a nice scale going from 0 to about 95. If we look at this one, what's wrong with that? See anything that's not quite right?
Age ones,
Zero. Well, first of all, the one on the left doesn't agree, and you very soon get a feeling for a data set when you're looking at it about how good the agreement should be visually. The age one goes up to age 200 for the synthetic data, which is not going to be very convincing. So if somebody got that kind of analysis data set, we provided it to a user, the first thing they would do would be delete it and say, sorry, can't be bothered using your data. So that's a possible outcome that we need to be concerned about. We have to be plausible. I'm just put in here the final agreement at the final analysis. This is something we can produce from our package, but I don't think it's relevant to my talk today. It's something which looks at the overlap of confidence intervals. So I just put that in because it was there. So let's talk about global measures. Basically, the global measures measure the distance from the synthetic data to the original data. And you can think of them as a measure of lack of fit to the original distribution. The Kuback-Leibler divergence has been suggested as a way of doing that, but that's actually a difference between distributions rather than a difference between empirical data sets. And the proposed methods for smoothing it don't seem to work very well. But the other two things that I'm going to talk about today are propensity score measures and measures based on cross-tabulation. So let me start with the propensity score measures. This is work that we did jointly with Joshua when he was visiting Edinburgh last summer. The idea of propensity scores is based on an estimate of the probability of being in one group compared to another. Probably most of you are familiar with the fact that it was devised by Rosenbaum and Rubin, and the idea there was to evaluate covariance in an observational study. So rather than doing adjustment for each individual covariate, you would do adjustment for the propensity score, which was supposed to incorporate all the differences between the two. It's been discussed, and for altered data, not specifically for synthetic data, by Wu et al. In the JPC in 2009. And we extended this work to look at how that method behaves specifically for synthetic data, because Wu and colleagues look not just at synthetic data, but other things like top coding and data swapping and so on. So what is it? You take, I'm introducing here a little bit of notation. You take the original data, which I'm calling Y, and the synthetic data, which I'm calling S. If you've got 6 variables, you'll have lots of lines, each of which will have Y1 to Y6, and similarly the synthetic data. And you add an additional column, which is an indicator variable, which is 0 for the real data and 1 for the synthetic data. And you attempt to use the things in the real data and the synthetic data to predict what the indicator variable is. What is this line's propensity of being in the synthetic data? There I've just used the data themselves, but actually you also can include interactions and any other term you want. So it can include a whole lot of other things, not just that. So you can, I'm going to mention in a minute, we're going to have a dimension of how many variables you've got in your predictor, which can be the original variables or combinations of them or transformations of them. So you calculate this propensity score difference measure, which I've tentatively called PSD, which is just the sum of the predicted values minus C, where C is the ratio, is the expected value. If you've got equal numbers in the two groups, then you're going to expect a half on average. When we were doing this before, we called this the propensity score mean squared error. But I've decided it's better not to divide by n, so I'm looking for a new name for it. So meanwhile, I'm calling it PSD. But I know that stands for the name of a conference as well, so that's a bit awkward. So anybody who's got an idea for a good name for it, I'd be very grateful. Turns out that this is approximated in large samples by a multiple of the deviance explained by the predicted model by the covariance over a null model that predicts every row as having C. And we first noticed that empirically and now been able to prove it asymptotically. And in fact, you'll see later the asymptotic approximation is very good. And it seems to work quite well even for moderate-sized samples. So the question that I'm going to address is, if we've got a measure, we'd like to know what we expect that measure to be. If our model was correct, what should we get for this? It seemed to me an important question, because it would be nice to have some kind of absolute measure of, is this good enough or is it not, just rather than saying just one measure is better than another, which is what they did in the Wu paper. And it's quite nice not to divide by n as well, as you'll see, because when you divide by n, you tend to get very small values that are quite difficult to read. But a little bit of theory. If you're synthesizing from some statistical model indexed by some parameter theta, then, in fact, in our case, our parameter vector is built up, if you think about it, from the parameters of each of the conditional distributions. So the whole parameter thing can be quite long and complicated, but it's still a parameter vector. Then you're generating the synthetic data from the same function, but with your estimate stuck in instead. That's one way of doing it. Some people call that a plug-in estimator, and it's what we usually do. But you can also replace that theta hat by a sample from the posterior distribution of the parameters given y, which is what was done historically in a lot of the papers that look at synthetic data. We could have an argument about that, but not today. Under these circumstances, you can actually derive the null distribution of the PSD. And we can show that if f of theta really was the correct model for y, if you could assume that y was generated from such a model, then obviously your simulated data are generated from f of theta hat, and you can show that for large samples, PSD is distributed as c squared into 1 minus t times k chi squared to the k minus 1. And the deviance criterion is c times that, which agrees with what was on the previous slide. So I hope it does. And in the most common case, where our two samples are equal, c squared into 1 minus c is just an eighth. So that gives us our first two utility measures, 8 times PSD, or 2 times the deviance. And both of these should, if the model is right, be distributed as chi squared with k minus 1 degrees of freedom, where k is the number of parameters that you've got in fitting your propensity score model. Not the number of variables, but how many parameters you've got, including all your interactions and everything else. So that's our first two. But when we started to get feedback from our users at the SLS, what we got is complaints about their tables not being quite right. That's what first thing that people look at when they do the analysis. So I thought, well, what's a better way to go would be trying to develop some kind of utility measure based on tables. It seemed a fairly straightforward thing to do. Oh, I'm sorry, I should have put in this extra one. These are the formula for plug-in estimators. If you're actually sampling from the posterior distribution, you need to include a factor of 1 over 1 minus c, or 2 for equal sample sizes, which is kind of intuitive because you're adding the same amount of noise again by doing that. Oh, sorry, I'm backtracking. When I had these extra slides, I should really look at what we've got here. How to model a propensity score is the key thing. Ideally, we would like to have all the main effects and interactions that are going to be of interest to whoever is going to use the synthetic data. But we don't really know that, so it would be tempting just to put everything in it, everything second and third order interactions. But you soon find that this leads to huge models which are not feasible and might not even be estimable. So that's one of the disadvantages. If our U statistics indicate a poor fit, we can have a look at the coefficients to see if the model, to see where the problem lies, and that's a good thing, and that works fairly well. But it's quite often quite difficult to relate the coefficients of propensity score models to what's actually going on in the data. Sometimes it jumps out at you, but sometimes it doesn't, because sometimes it's 2 or 3 coefficients and you don't quite work out how they work to go together. And I think an open question is how we should advise people to use these propensity score models. So hopefully this will now take me on, yes, to tabular measures of utility. Supposing we use our data, we've got categorical data, or if we've got continuous data, we can divide it up into, we can categorize it into groups, which is what one often does at the start of an analysis. And so if we form tables, we have counts x1 to xq, assuming we've got a table, which could be a table of many things by each other, but the table has q cells altogether. It could be a 2-way or a 3-way table. We've got the counts from the y variable, which I'm calling x, and the counts from the synthetic s variable, which I'm calling z. So an obvious thing to do would be to calculate a chi-square distribution for this. And I think you would probably agree that for a correct model, that should be chi-squared into q minus 1. Here, xi has the role of the expected variables. The original data has the role of being expected, because if the model is correct, then z, the synthetic data, will be generated from a multinomial with parameters x over n1, where x is the real data. So there we are. That formula assumes equal sample numbers. If you don't have equal sample numbers, then you have to adjust the x to make it into the correct expectation. But the formula still goes forward and it's still chi-squared. So that's the idea. But there's a bit of a problem with this. If your model is correct and your true values xi have a cell with 0 on it, then you're never going to get any synthetic data in that box. But if it's not correct, then when zi is non-zero, you can end up not being able to estimate chi-squared because it's got a 0 on the bottom line. No, I said that the wrong way around. Zi is 0 when you're creating synthetic data for from real data which has a 0 cell in it. And it can happen very easily, as we'll show in some examples. We can't ignore these cells, because that actually could be the most important part. So for example, if we have some real data that have a table with a structural 0 in it, and we generate synthetic data with several hundred observations in there, we sure as anything want to know about that. So we want that to contribute to the utility measure. And that's happened to us quite a bit in practice, that there may be structural zeros we don't know about, and which we ought to try and fix by setting rules when we're doing the synthesis. So I then found a paper that had addressed just that question in a journal called Geographical and Environmental Modeling, which I'd never come across before. And it's a paper by Voas and Williamson from 2001, which suggested replacing xi in the denominator by xi plus zi divided by 2. So you just put them in the average in the bottom. And it generalizes to something else. If you've got unequal sample sizes, then you have to generalize it to that to make it sensible. Now, that's not the only choice. And I remembered some papers in a book by Reed and Cressy that talked about something called the power divergence family of statistics. How many of you knew about that? You did, Chris. Anyhow, I had sort of vaguely heard of it, and I found it. And that's the form. And it gives you a whole bunch of statistics indexed by lambda. And you usually reckon you shouldn't go outside that sort of range for lambda. You've got Pearson's chi-x, I call it x squared, with a lambda of 1. The deviance has a lambda of 0. And then there's the Freeman-Tukey statistic of -0.5. And there's another deviance statistic that's it reverses the role of the observed and the expected, And there's Neyman's x-squared statistic, which puts the observed data in the denominator of your chi-squared formula rather than the observations, rather than the expected. So this is a whole range, and looking at this table, what happens to them when your xi or your zi are 0? If your xi, which here takes the role of being the expected, is 0. I got this the right way around. I think it's the wrong way around, isn't it?
I think so.
It's the wrong. Oh, I just changed it because I thought it was the wrong way around. Right, forget that bit there. If the expected is 0, wait a minute, maybe it is right. Oh, which of these is which? Let me stop and think. Zi here is the observed. Xi is the expected. If this crosses and takes should be the wrong way around, I should have left it as it was. You can only get the Pearson's chi-squared and the deviance and those sort of things if you don't have a 0 expected. And the other way around, you can only get the Neyman's chi-squared if you don't have a 0 observed.
So just
any of your
really
cells.
quick clarification, because when lambda's 1, then you got 2 divided by lambda over 1 minus lambda. That messes it up, doesn't it? Because it's 2 over 0 then. I mean, how does that...
You have to look at the limit.
Oh, right, okay.
It's the limiting distribution. For the deviance and the alternative deviance, you have to take the limit as lambda goes to 1 and the lambda goes to 0. It's all in Reed and Cressy's book.
Right, okay.
The important thing about this is that there is a member of this family, the Freeman-Tukey one, which is at -1/2, which has this rather nice formula, which in fact you can use for either. I must admit, I had never come across this statistic before. Has anybody ever used it? That seemed rather useful. Anyhow, that's our next option. So that increases the number of utility measures we have. We've got all of those ones that we could take from the power divergence family. Notice that the Voas and Williams is not actually a member of the power divergence family because it's got this average on the bottom. All of these statistics are distributed as chi-squared with q-1 degrees of freedom asymptotically. And it turns out that you can also take tabular data and reformat it in long format and calculate a propensity score from it, obviously. And it turns out that the Voas and Williams chi-squared is in fact identical to the propensity score model. It's not just asymptotically the same, it gives you exactly the same formula. And it wasn't until the beginning of this workshop that I realized this. So it's really helped me on to think through it. But it's not a member of the power divergence family. So let's summarize. Yeah.
Quick question. Can you go back a couple slides to the table of all the different measures?
Yeah.
So if I understand you correctly,
So
the reason that it's good, the Freeman-Tukey is good, is because either the observed can have 0 or the synthetic can have 0?
Yeah.
So what is the situation if you're using what I assume would be some type of multinomial model that you would have 0 observed but actually draw synthetic counts? Because if you have no original counts, when you have
synthetic counts.
0
That's the
probability
case
of that?
when your chi-squared would give you wouldn't work.
No, but I'm saying when would that actually happen when you're synthesizing?
Well, I'll show you an example, but I'll just explain it briefly. Imagine you've got a two-way table which has structural zeros in it, and instead of synthesizing it from both of these variables, you just try to synthesize this one and this one independently.
Oh, so you just do a really bad synthesis or something?
Yeah, that's
Okay.
right.
Well, but sometimes you might have like a four-way table and you only synthesize on two-way margins, and then so then it sometimes it may not be as that probably
that's the example, but
yeah.
that can often be embedded in
Yeah.
a much more complicated table. It will never happen if your model is correct.
Well, so if it's saturated, it
If
will
it's
happen.
saturated, it can,
Yes.
right? Okay, I
Yes.
see. So you're saying for not
Yes.
saturated, okay.
Yes. Well, I think it's more general. It's if you're actually simulating from the correct model. Because-
Well, but I'm just saying if it's saturated, right, then you have 0
Yeah.
expected, so you can't.
Well, but there's an interesting point because doing this with sorry, I don't want to digress, but because if you do it this way, then you will always get a zero inflation. Because if you say a real zero always stays synthetic zero, but you're always going to get some zeros coming through because small probabilities of count. So then you're always going to have too many zeros. So it's not necessarily a good thing that a real zero should always stay a synthetic zero from the utility point of view as well. So,
No,
I mean,
that's right.
Yes.
Yes, no, I mean, it would not be, you wouldn't be synthesizing correct. I should say that if you've got zero in both, you don't contribute. What Voas and Williamson and I have been doing is dropping the number of degrees of freedom by the number of double zero tables, and that seems a sensible way to go. And that's fine if you've got structural zero, but it could happen when you haven't got a structural zero, I suppose. But it doesn't seem to interfere with things too much. Right, so moving on, I'm wanting to, we've now got all these different measures of utility, and I'm going to illustrate them for some tabular data, just taking 3 variables from the 1901 census from Lothian, Scotland, of which there are 355,000 records. And I'm taking 3 variables, sex, marital status, and relationship to the head of household, which produces a table with 80 categories. And it has 8 zero cells. Some of them are obviously, or should be, structural zeros. For example, a lodger's wife should be married, and a spouse should be married. But there are others where it's not clear whether it is a structural zero or not. As well as the 8 zero cells, there's 1 cell of 2, and 2 each of 2, and 3, and 3 more under 10. So you've got a table which is very sparse at one end, but then quite quickly gets rather large because you've got to fill up your 80 categories with 355 observations. So you can do what I call a correct synthesis. You're assuming that this table, and that's what you do in most statistical analysis of this sort, you're assuming that this table had been generated from a multinomial distribution with probabilities that correspond to the 80 cells of this table, except for the zeros. So the way we do it in synthpop is to stratify by sex, first creating the synthetic sex variable, and then within each stratum we synthesize the head of the household from the sex, and then the marital status from the head of household. I shouldn't say and sex, that shouldn't be there. From the head of household, so you've got a 2-way relationship within that. And it's equivalent to sampling from the full cross-tabulation with 72 non-zero cells. So that's really synthesizing from the correct model. So calculate the utility models by making the tables of the original synthetic data. The original data has 72 non-zero cells, and the synthetic data, because we're doing it from the correct model, has 72 non-zero cells as well. We calculate the utility measures from the counts, the tabular ones, and then make it into a long variable and calculate the propensity score values. In fact, we've already got one of them from the Voas and Williamson formula, but we've got the other deviance one as well. When we fit the propensity score model, we know it should have 71 degrees of freedom. There are 79 coefficients, but 8 of them are inestimable. So that all makes sense. So let's have a look and see what some of the results look like. This is for the correct model. We get all the U's because there are no zero cells. We've got 71 degrees of freedom, and you see they're all giving 66. Now the expected value of that should be 71 with a standard deviation of around 12. So all the utility measures have very similar values well within the expected range, which is a relief. But what happens when we do a wrong synthesis? That's potentially more interesting. This is the wrong model. Data synthesized independently in each column. All the cells that are 0 in the original have synthetic counts in them, which is not surprising. We already have a few cells with 0 in the originals, but because they've got some synthetic data in them, they contribute to the propensity score models, to the utility measures. We can only get 3 utility measures here, the Freeman-Tukey and the Voas-Williamson or propensity score, and the deviance from the propensity score. And they all give around over 5, the best one is 500,000, which one should be 71.
Why can't you get the Alt-Devlin naming chi-squared? Sorry?
Yeah.
Sorry?
Why can't you get the Alt-Devlin's naming chi-squared? Because presumably you don't have any zeros in the synthetic table.
You've got data in the synthetic table and you've got a 0 in the real data.
Doesn't that rule out the top 3?
No.
Not the bottom 2.
It rules out the top 3, and the top 2 are, these ones are ruled out for different reasons.
Okay.
Let me work out which one. Top 3 are ruled out for the reason I said. These Alt-Dev and Neyman are ruled out because we've got think through this one. We've got 0 observed, where we've got, is that right?
So you have both ways, you're saying?
Yeah.
You have some 0 observed with non-zero synthetic and some
Yeah,
zero
because
synthetic
you've
with
got
non-zero
some
observed.
0 observed and they've got synthetic data in them.
So it ruled out everything except for the.
Yeah.
But you don't
that's
have any zeros in the synthetic table, do you?
Yes.
Oh, you do? Okay.
Yes. Those two.
Just it's not necessarily a
Yeah.
correspondent.
No, you have some of each.
Sure.
This is such a noise, you get that all the time. Yeah. I haven't really worked out how many you've got in each one. I didn't really think about it. We now have 79 degrees of freedom because for these other measures, because we've always got a 0 and a something, or a something and a 0. So we've actually got more degrees of freedom because these 0 and something cells have contributed.
So can I just quickly ask, if you have a 0 and a 0, so if a 0 observed matches 0 synthetic,
Yeah.
then will all these approaches work? Because otherwise, in large data
If they
sets,
all match.
if they all match, yeah, because otherwise,
But
you
as
get
soon
to-
as
yeah.
even one doesn't
Right.
match, we're away.
Because otherwise you're going to have problems, right? Because in these large data sets, you're always going to have zeros. I mean, say,
Of course, yes. But the Freeman-Tukey and the deviance measures, they will always give you an answer. But the others will usually not give you an answer. And here, none of them did because the synthesis was so bad. Now, let's look at something that's a bit better. If we, instead of synthesizing completely at random, we synthesized each variable as a logistic regression. It doesn't preserve all the interaction. The final model will depend on the order in which you put the variables into the synthesis. And we have 6 possible orderings, so we've actually got 6 choices of model here. So I've got marital status, sex, and relationship. So MSR says do marital status first, and sex second, and then relationship ahead of household. And there are, I'll show you on the next table that there are 6 such variables. Now we're no longer in the hundreds of thousands, but we are in the thousands. It's still not very good. For MRS, we never get the Neyman chi-squared and the alternative deviance for these models because we've got zeros in the original data. And for none of these zeros, none of them did we actually have zeros in the synthetic data, which is perhaps not surprising with a data set of that size. We can always get the Freeman-Tukey, we can always get the other matters. And looking across the table, you can see that some models seem to be doing slightly better than others, but they're all pretty bad. That chi-squared would not be considered to be acceptable. And we'll come later to what is acceptable in terms of how many times your expected value it should be. I don't want ever to think of these things in terms of significance tests, because we never really think that we can get the model right. But it's merely a measure of how bad is But this next one's quite a bit better. If we use cart instead, in fact, the third one along is really not bad at all. In this case, we're very seldom going wrong, where 71 is what we would expect if we had the right model in terms of the degrees of freedom. We've only got a few cases where they're not giving us the right answer. We're still getting values in the cells that should be 0, but it's a lot better. And for 71 degrees of freedom, I would, if I was evaluating that synthetic data, I would think any of these models were fine. They look okay. So I was quite pleased that actually seemed to work. And this goes along with our general finding that CART models find the interactions that matter. They don't necessarily give you a perfect answer, but for this one, I think it's pretty good. It obviously gets a lot harder when you get up into more dimensions. But for this one, I thought it was doing well. So which utility measure should we choose? For tables, we've got a choice of 3, and for other cases, 2. Though perhaps there is an equivalent to the Freeman-Tukey for the propensity score, I don't know. I haven't had time to think about it. But in fact, from the work on the real data, it doesn't seem to matter very much. I also did a simulation study, which I did before I looked at the real data. And it was really to look at what happens with very large samples. And this was with a table with 10 cells and a huge number of observations. I think it was 50,000. Initially, making a random partition of the probability of being in that and simulating and synthesizing from the correct model for each one. And this is what the comparison of the different, under the correct model, all these different statistics look like. And I think you would agree that's pretty good, just visually. These are the ones starred are the ones we can measure for everything. The propensity score and the Voas and Williamson are, as expected, completely linear, but the others are really not bad at all. And one would, in fact, make very little choice between them. But of course, that's if the correct model is there. And it's perhaps more interesting to look at the case where you have an incorrect model. And in fact, this next plot, which I'll show you, is not just one incorrect model, it's a whole series of incorrect models. Because what I did was I simulated from a random subdivision of the probability into different bits. And then, so it has a different distribution for each simulation, but I evaluated it from an equiprobable model. So, looking at that, you see that with the wrong model, there are some differences between them, but the ones that we're interested in, the propensity score deviance and the propensity score, here, still pretty good agreement. The Voas and Williamson and the Freeman-Tukey, that's this one here, is also in pretty good agreement. So that suggests that from the simulation, which may not be relevant because it's a very large sample which doesn't have any small cells, which is probably not what we're going to get. But perhaps tells us something about it. Now, if the statistics no longer agree, they have potential for one to have better power than the other. And you would think if these all have the same null distribution, then in some crude sense, a large value of the statistic will tell us we've got a more powerful way of looking at utility. And the mean for the simulations show that actually the chi-squared, some of these ones we can't usually compute, seem to give us the largest values. But the other ones are not bad, and really down at this end, the Freeman-Tukey gives us about 2,000 on average, 1,900 there, and the propensity score a little bit less. But suggests that this random set of alternatives, the chi-squared may have better power, and that sort of agrees with some other studies about chi-squared tests. Of the 3 measures that work well, there's really nothing to choose between them. But clearly that's not particularly relevant to here, and perhaps we should be looking at some other way of doing it more realistically. So choosing which utility measure, it really doesn't matter for simulation study either. So take the easier one for tables. This is the Voas and Williamson measure. For propensity scores, the more important question is which model to use. Should it be targeted at some of the variables of interest, or should it be trying to cover the whole range? My personal, well, just in the same way as when you're doing tables, you can't do a table of everything by everything. You have to select your tables. Should you select all two-way tables and then just do a range and see if any of them are really bad? I think that's kind of equivalent to doing a propensity score model with all first order interactions in it. Is that a possible way forward? Or should you speak to your researcher to find out what it is they're really interested in and perhaps take your first order and second order interactions with whatever their outcome variable is? So a lot of questions there. Now, what about CART? It worked very well for doing the synthesis. Could we use it as a propensity score model? The problem with that is that these formulae for the null distributions assume a fixed model and assume that you know it. And when you look at the results of a CART propensity score model, they look completely different because you've got this model selection thing. And you get a very different set of results. But Joshua suggested last summer that we could use a permutation model to get the null distribution of the propensity score. And that seems to work quite well. So basically, if that's how you calculate the propensity score, you simply take a set of random permutations of your indicator, get the distribution of that many times, and that gives you the null distribution. Clearly a number of assumptions in there, assuming that in some sense the two models are equivalent, but it does seem to work reasonably well. That's something which we're in the process of implementing in our utility measures in our package. And again, we need to look at it a bit more. So we've got some tentative recommendations. Perhaps look at important tables. Ask the user what's of interest. Perhaps use CART models for propensity scores. Question which I just thought of just now is, can we examine the trees that we get out of the CART models to see where the problems in the synthesis use? Have you ever tried that, Joshua?
No, but I'm sure that you can do that one way or another.
Yeah, that would be an interesting experiment to see if it works. Something that you keep coming up when I'm thinking about this is remembering George Box's remark that no models are, all models are wrong, but some are useful. We're trying to find useful models. We don't want to get perfect agreement. But these models can tell us when synthetic data are not useful. You saw how bad, things can get really bad, and you can sometimes find out why, which is encouraging. But I think in terms of the interpretation of these things, we don't want to think of them like significance tests. I think it's much more useful to present them as ratios, and I've been thinking of presenting them as Z statistics to say that gives you a little bit of evidence without actually putting the p-value in, but maybe that's being a bit too inferential. I don't know. Ratio is good though.
On the CART model, is this what you're thinking of? I was thinking a while back about, like, if you fit a CART model and then you've got the leaves, and then you can look at because you've stacked the data right there,
yeah.
And then you can look within each leaf to see what proportion are observed and synthetic.
That's right. And when you actually look at the predictions from a CART model, you get far too many zeros and ones for precisely that reason. And it might be that the CART model should be adjusted, perhaps to have slightly bigger leaves for that.
Well, it depends on how much you grow your tree.
Yes, that's true.
There's a variable importance measure that I've seen in the literature on carts. So it looks, because the way that the cart works is you look at something like the Gini coefficient or something like that, and so they will add up all the utility that you gained by splitting on certain variables, and so you sort of get this figure with the amount of utility that each of the variable
So how
has.
much it contributes. That
Yeah.
sounds really useful, actually.
Yeah,
Give
I
us
can
that
send you the reference. Yeah.
That would be great. Thank you. Yes. Anyhow, just before, that was really all I have to say. But before I stop, I thanked at the beginning Mark and the rest of you for giving me the privilege of being here for this week. I also have to thank my family, because when I foolishly offered to give this seminar a couple of weeks ago, I had realized that in between I had a week to spend in Malta with my son. So they had to put up with me sticking my nose in a notebook and a laptop for quite a lot of the time, when I should have been taking part in family activities. So hopefully if any of them ever watch this and get to the end, they can hear me thanking them. As a reminder, I've got a box of Maltese biscuits that we could share, but perhaps we can have some more questions before that.
Thank you very much. So are there any questions? And if anyone listening wants to email me questions, that's fine as well.
Audio.
Sorry?
There's no audio, like speaking from.
Coming from like the ether sort of thing. Wants to go?
Yeah, so I'm interested in propensity score modeling for causal inference. So I'm thinking, what's the difference for the propensity score model for this purpose with, I mean, all the guidelines and all the results that are given within
Well, I
causal
think there's a lot of
inference?
similarities, because
Sorry.
I think there are a lot of similarities. Do you think of any differences?
No, I mean, they build, most of the guidelines build on the balancing property of the propensity score. You fit the model, you evaluate the balance, and you fit.
I mean,
and
here
so on.
we're seeking a bad fit.
I think so. The motivation came from that, right? So the Rosenbaum and Rubin paper said
Yes.
if two units have the same value for propensity score, then they come from the same distribution. So
Yes.
so that's where the motivation is. So if you have the same values of propensity scores, you have the same distribution.
And if in a causal inference study you have a very low propensity score, you don't need to do any adjustment. Do you? Well, if you have a very constant propensity score without much variance, then you're okay. Here, we're looking at variance of propensity score, you see.
Well, I think one difference is that in the causal inference framework, you're using the balancing as an evaluation of your propensity score model, which we don't have here. And that's why we have this open question of what is the right way to choose a propensity score model, because we don't have this built-in evaluation criteria, which is the balancing.
Yeah, that's right. It's a very different sort of application. Do you ever use these sort of card models?
Yeah, I mean, they are well used in the causal inference settings.
Do you worry about overfitting?
No, not really.
Yeah. Because, I mean, we use them a lot in synthesis, and I don't think you need to worry about overfitting there, because any noise just appears in the noise for the synthetic data.
So just to follow on to that, because I was going to ask this, but because you just mentioned it, is there ever an issue that anyone's encountered with separation? Because if you overfit, then you're more likely to get separation problems, aren't you, in this sort of setting? So I don't know, because it's sort of an issue that can happen with binary response models and stuff. So I don't know if that's something that might.
It need to be really bad.
Well, you need to have but if the more variables you get, then eventually it'll happen, right? I mean, the way it's set up. I mean, if you have, I don't know, maybe your data sets are so huge that it's not unlikely, but I
It
don't know.
doesn't have to happen eventually, right? If you have,
Depends how the size of the data set increases with the number of variables.
Well, I mean, yeah, fixed sample size, but if you have, because with big data, it's what we've been talking about this week. I mean, it might be something that is, I don't know, I'm not sure.
Well, I think how big the propensity score model should be is a question. which
Because you have the more
shouldn't be
things you
used,
put in.
right?
Sorry, Chris.
Yeah, lots of very nice things there, Gillian. But yeah, I wanted to follow up on this, how complex the model should be. So, I mean, my memory of sort of early days of synthetic data, the biggest failures were in subsets of the population that when people ran analyses, multivariate analyses on subsets defined by some of the variables where that model was quite different from the population, they could do quite badly. So that what on the face of it seems quite critical is to get the interactions right in your propensity score model. So it is to do with the different variables and how they're related in terms of the propensity. So in some ways it's good to have procedures that detect with decent power these sort of deviations from these sort of propensity effects in subpopulations and relationships. So, but I don't. At the same time, sometimes if you're looking at quite small subpopulations, they're presumably going to get somewhat dwarfed in these global measures in goodness of fit tests and so on. So I'm not quite sure. I'm sympathetic to when you said that you actually talk to the users and say, can you tell us some of the analyses that really matter to you?
We've not really done that.
And
but I can see
at the
that's
same
the
time, you
reform.
know that in the way you've constructed your model by a series of conditional distributions, you're presumably going to get those conditional distributions reasonably okay. It's the other conditional distributions that
Yeah,
you might
and
get.
backwards as well, because actually everybody, whenever we send in papers about this, they say to me, but what about variable 10 can't be related to variable 1, but it is when you think about it, because it's been in there as a predictor. But one of the things we've been doing recently has been developing the idea of being able to stratify before you synthesize. And that seems to be very helpful for computational reasons as well as anything else. You divide your data into strata, and that way you preserve all the relationships between your stratifying variables and their interactions.
So
with
if you
everything
were
else.
looking at labour market behaviour, you might, I suppose, separate women and men or something.
Well, you usually separate many have
So that,
different
so
animals.
you don't want to
but
be
actually, more
shooting across
importantly, in a
genders.
longitudinal study, we've been stratifying by inclusion criteria. That works quite well because if you've got longitudinal data with missing data in a funny pattern, that helps a lot because if you have big swathes of missing data because people miss the waves in the survey, so that helps to simplify things quite a lot. But it also, I think, is a more sensible way of looking at it because people that answer all the surveys are probably a bit different from those that just come in anyhow. Seem to work nicely. A sensible way to go. And of course, it reduces the dimensionality of the thing, and the size, which can be really problematic.
I have a non-statistical question. I was just curious. The head of household, how is that defined?
It's the first person on the census book.
Oh, okay.
But they were supposed to take, they nearly all take the man.
Right, okay, but technically it's the person who's filling out the form, but everyone just puts the man if there's one in the house.
Well, sometimes when it's a woman, they will fill things in, though it gets recoded to things like wife, head, absent. But that gets recoded in the ICM.
Well, was that a 1901 census? Not nowadays, right?
Yeah.
Oh, 1901, okay, yeah.
But that still happens now.
Really?
Yeah.
Of course.
But there are a lot, actually, this relationship to head of household have a lot of small values, like mother-in-law to the lodger. That kind of thing.
That's a random one.
But I think some of these have been coded out, but it's quite fun to look at the data. It's actually quite entertaining.
Freeloader.
So,
It's one of the data set, this is part of the same data set that we might use for a test.
right, so this data set is now sort of public because it's so old?
No, it's
still
I'm still
restricted?
actually, well, I need to answer that question from Mark, because if we want to use it as a test data set, it's available from the integrated census microdata.
Okay.
You can download it in bits, and there are a lot more variables. Well, there's obviously a lot more than these 3, but there's a lot more than the 14 we discussed this afternoon.
Because I think we have to check on our census that like we agree the data to be available to everybody. Like,
Well, they didn't,
100
do
years
that
later.
in 1901.
Right.
So anyhow, even if they had, it would have been 100 years later. But the data were not filled in forms, they were filled in enumerators books, which were then transcribed. And if you sign up to a genealogy website, you can see the original forms.
Because I attended a training course, ONS, for this VML type training, and they said that I think under the law, once people are deceased, then the data is no longer confidential.
Well,
So,
data protection doesn't apply, but I think, Mark, is that not?
so number 1901 should be all right. Well, no, I think it's only once.
Everyone in the family is like everyone.
Oh, what about no? If you were alive in 1901, I don't think you. Well, I
You would
suppose
be
it might
alive
be.
now, but your children might be, and they might not want to know what you've
And I think
what
it
your
applied to the.
occupation was.
I think it applied to the person. I don't know. Do you know?
Sorry, what's the exact question?
So, well, I mean, if I thought that the data is no longer confidential once a person is deceased. So
Yeah, so the DPA doesn't apply. Other forms of legislation might apply.
okay.
Human Rights Act, for example, still applies. Right.
Okay.
So yeah, it's complicated, but there's a general 100-year rule principle which applies to any data, which is just a
It's a government thing, isn't it?
yeah, it's a government thing. So any data that's held by government will be automatically released, providing it's it's resourceable.
Are there any other questions? Okay, well, let's thank Gillian again.
And please have a Maltese biscuit.
Does that mean malt comes from Malta? Or